doubts, so maybe let's discuss together.
So even one was then one of them is so you have to figure out then this will become 3 times 1. Can I just call the multiplication?
So when we are tracing the recursive method, essentially we are doing the same thing as when we are doing the iterative method. We just need to take into account what is the operation that we are tracking. Now, in the case of this, because it's a power, right? So power is a series of multiplications. So we are tracking the multiplication operations. Now then you are given a problem here, x equals to 3, n equals to 16. What is going to be the complexity of power 1? So this is the recursive power 1. The base case is n equals to 0. Otherwise, we are going to do recursive reduction to n from n to n minus 1. So which means that if we call P1 16, P1 316, right? So here the n is 16, 16 is not 0, so we're going to go on and call n minus 1, which is 15. So when 15 is going to call 14, 14 is going to call 13, 12. Now when do we stop? Now the last time where we are going to do recursive call is when n equals to 1. So when n equals to 1, it's going to call another time to 0. So 1 is going to call to 0. So by the time we come to 0, that is the base case. There is no more recursion, right? So then we will start to return. Now, we are going to do this multiplication every time we make a recursive call. So that means that there is 1 here, there is 1 here, there is 1 here, there is 1 here, right? Now, does 0 make any more multiplication? No, right? 0 doesn't make any recursive call, so it doesn't do any multiplication. So there is 1 from 16 all the way to 1. So the number of multiplications is 16, right? Now, if it is n, the number of multiplications that you have, so for example, this is P1. So say k to the power of n. So the k here doesn't actually matter, because the k doesn't affect the recursion at all, only the n does. And the number of multiplications we will do is going to be n multiplications. So then the complexity is going to be O n. Alright, any clarification about this one? Before we go on to the next one. So the next one, we are looking at power 2. Now what it does here is to evaluate the same number, but we are going to make different cases here. So when it's 0, so it's a base case, we just return 1, because anything to the power of 0 is 1. Then we're going to look at whether the n is even or odd. So it is even, then we are going to divide n by 2. So there is one multiplication here. Otherwise, we're going to divide n by 2. And there's going to be a leftover, right? Because if it is an odd number, so for example, let's say 15. You divide by 2 is 7. So 7 is still sum up only to 14. So you need to add one more multiplication to the here to bring it back to the original power here for odd numbers. Now we're going to do the same kind of analysis for power 2. So we start from 16. So 16 is going to come here. It's not 0, so it's not a base case. So then we're going to do recursive call, but it's a matter of which one. So we're going to check whether or not it is an even number. So 16 mod 2 is 0. So it is an even number. So then it's going to call this, right? This and this, right? So it's going to make 2 calls to 8 and 8. So there is 1 multiplication here. Now each of the 8 is going to make 2 more multiplications. So there is 1 and 1 here. And each one of these is going to have 2 more. So there's a 1, 1, 1, 1 here. So each of these again is going to have 2 more. Do we still have any more recursive calls?
Yes.
So we have one more time, right? Because 1 here is not yet the base case. So we're going to come into this condition. So we're going to have 2 calls to zeros. So this is the same for all of them. Now, how many multiplications do we have here? Because by the time we come to 1, 1 calls 2 zeros, but there is still a remainder of 1. So in that case, we're going to have 2 multiplications at the bottom layer here, right? So that means that each time we combine 2 zeros into 1, there are 2 multiplications, and so on. So if we count how many, so there is 1 here, there is 2 here, there is 4 here, there is 8 here. So then we have 16 ones, right? Each of them has 2. So we have 16 times 2, so 32. So the total number will be, so in this case, 47. Right, so the bottom one has 2 each. 2, 2, 2, 2, 2. How many of them? There are 16 ones. So they're going to be 32. But there's 8 here, 40, 44, 46, 47. Alright. Now if we are going to generalize this to n, because we are going to determine the complexity, so we need to sum up this number. Now what is this number in terms of n? Now let's first make an assumption that the n itself is a power of 2, like 16, right? Now at the end, we know we're going to have a series of ones. And how many ones are we going to have? We always have n ones. So we're going to have n ones. And each of the ones is going to have 2 multiplications. So at the bottom, we always have n times 2. Because power n, you can always divide it all the way until you get 1, 1, 1, 1, 1. And at the bottom, there are going to be n of them. And each of the power 1 has 2 multiplications because of this one and this one. So you already have 2n. Now, for the remainder, now we are looking not at the ones, we are looking at the 2's. Now, how many 2's are there? Well, because originally the number is n, and we say 2, 2, 2, how many 2's? They're going to be n over 2 of them. And assuming for the moment that they are even, then there is only 1, right? Now, then we go to the 4's. How many 4's are there? They're going to be n over 4 of them. And assuming they're even, it's going to be 1. N over 8, all the way until we get to 1. There is always a place where we get to 1. So then we just look at this one alone. It will be 1 plus 2 plus 4 plus 8 all the way to n over 2. So this 1 plus 2 plus 4 plus 8 all the way to n over 2. This is equals to n minus 1. So why is it n minus 1? So we did this exercise before. Let's assume this is x. So we're going to take double of that, which is 2x. So n over 2 multiplied by 2 is n. And we have n over 2 all the way. So in this case we have 2 plus 4 plus 8 and so on. So then we're going to subtract them. 2x minus x is x. So we're going to take the top one minus the bottom one. 2 minus 2, 4 minus 4, 8 minus 8, n minus 2, n minus 2. We are left with n minus 1. So the whole thing is n minus 1. So which means that the sum here is actually n minus 1. So if this is equals to n minus 1, then the total sum here is going to be 2n plus n minus 1 is 3n minus 1. Which is, when n is 16, then it's going to be 3 times 16 is 48 minus 1, which is 47. Now, this is assuming that this is power 2. But you don't always get power 2, right? So somewhere in between, it may not be power 2. It may actually be some even odd numbers and so on. But even if you increase the expectation that it's not 1, 1, 1, if you say that these are all odd numbers, then it's going to be 2 times 2 times 2 times 2, right? So instead of 1, it will be 2. This whole thing is still going to be n minus 1. So then you still have 2n plus 2 of n minus 1. So the total sum will be 4n minus 2. So the number of multiplications will be between this number and this number. This number assumes that at every level is always odd, which of course is not always the case, right? So that is overestimation. But in either case, what is a big O? It's going to be ON. So it means that the complexity of the power 2 is still ON.